Hello grade 10s, welcome back to another video with me, Miss Martins. We're going to carry on with going through our chemistry exam questions. We're busy doing November 2019. If you haven't seen part 1, click the link above. In this video, we're going to focus mainly on the quantitative aspects of our chemistry section, which is stoichiometry. Just as a reminder, we always refer to the formula sheets and the physical constants as attached to our paper. We always write down the formulas as given on the formula sheet, and then we rearrange if need to, and then we always refer to the periodic table. Okay, let's jump right in. Consider the compound Al2SO43. Write down the name of the compound above. For 1 mark, easy marks, Al is aluminium, SO4 is sulfate, so my compound is aluminium sulfate. Then they want us to define the term molar mass. We know that molar mass refers to big M, and it can be seen in the following formula. Baby M, which is mass, over big M, which is molar mass. So in order to define molar mass, we know that molar mass is the mass of 1 mole of a substance, and it's measured in grams per mole. In our next question, they ask us to calculate aluminium sulfate's molar mass. So as you know, molar mass is big M. We need to refer to the periodic table in order to calculate molar mass. So what I mean by the periodic table is we need to look at the periodic table, we need to look at the elements in the compound, and we need to look at the atomic mass numbers associated with each element. So we've got aluminium, and we know aluminium has an atomic mass of 27. Sulfur has an atomic mass of 32. And then oxygen has an atomic mass of 16. Now we say, okay, cool. In my compound, I have 2 aluminium atoms. So we look for the mass of aluminium and we multiply it by 2. I have 3 sulfurs because of the 3 outside the bracket. So I look at the mass, the atomic mass number for sulfur, and I multiply by 3. And for oxygen, I have 4 times 3. I have 12 oxygens. So let's do that. So there we go. And I've color coded to show you why I'm multiplying by the things I'm multiplying by. And if you do that on your calculator, you get 342 grams per mole. Remember your units or you're not going to get your mark. 5.3.2 wants the percentage composition. Now, essentially, this is the percentage composition by mass. So looking at the mass in terms of atomic mass, how much of aluminium sulfate is aluminium versus sulfur versus oxygen. So if we want to look for the percentage composition, what we do is we take the mass of the element in the compound, so the mass of the element, divided by the total mass of the compound, which is the molar mass, so that goes underneath there, and we times it by 100 because we want percentage composition. So when we're looking for a percentage, we times by 100. So because we've got aluminium, we've got sulfur, and we've got oxygen, we're going to do 3 little calculations. To look for the percentage of aluminium in aluminium sulfate, we're going to take the mass of aluminium divided by the total mass. So as we said, aluminium, there's 2 atoms of aluminium, and the mass of each aluminium is 27. So it's 2 multiplied by 27. That's the mass of aluminium only in that compound, divided by the total mass of the compound, or the complete molar mass, which is 342. We're going to multiply that by 100. That'll get us the percentage of aluminium. Then we're going to do the same for the percentage of sulfur. So we're going to take the mass of sulfur. So we know that sulfur's mass is 32, and we have 3 of them. And we're going to divide that by the total mass, 342 times by 100, because we're looking for percentage again. And then we're going to do oxygen. So we know that each oxygen has a mass of 16. That's the atomic mass. There's 12 of them, divided by the total mass of the compound, 342, and we're going to times that all by 100. So it's always mass of elements in the compound divided by total mass. Now just remember, mass of element means the mass of elements in the compound. So I know aluminium is 27, but we times it by 2 because in this compound we have 2 atoms, 2 aluminium atoms. And there's my 3 percentages, 15,79, 28,07%, and 56,14%. If I add up those 3 percentages, I should get to 100. It might be a little bit off because remember, these can be rounded off to 2 decimal places. The next question wants the number of moles present in 85.5 grams. So number of moles is N. 85.5 grams, that is baby M, and we have big M. So you should know the formula that we're going to use is number of moles is equal to mass divided by molar mass. That is the formula we're going to use. If you want more information about these, when to use what formula, watch my previous video on stoichiometry, linked above. Okay, number of moles present in 85.5 grams. So my mass is 85.5. My molar mass, again, is what I worked out earlier, 342. And then I get 0.25 mole. There we go, 3 marks. Formula first, substitution, answer with units. Now the next question is a little bit more difficult. So they want the number of aluminium atoms present in that same mass. So using that mass, we worked out that the number of moles present is 0.25 mole. Now they want the number of aluminium atoms. When you see calculate the number of, you should think about big N. You need to think along those lines. And we know the formula involving big N, which is number of particles, compounds, atoms, is this. Right, so this is what I'm looking for. This is my prize. This is what I'm going for. Baby N we have from the previous question, and Na is called Avogadro's number or Avogadro's constant. That is 6,02 times 10 to the power of 23, and that is given on your formula sheet, as you can see over here. So if I substitute the 0.25 over here, and I'm looking for big N, and I substitute an Avogadro's number, do you see how I'm using brackets? The reason I'm doing that is because when it comes to scientific notation, it's often a good idea to use brackets. Then to get big N, we say 0.25 multiplied by Avogadro's number. When I do that, I get the number of aluminium sulfate molecules. So 1,505, I'm not rounding off, times 10 to the 23, that is the number of aluminium sulfate molecules or compounds. That means I have that many of these compounds, but I want to know how many oxygen atoms, sorry, not oxygen atoms, how many aluminium atoms I have. So I explained this in my previous video. So if you want to see that video, I'll link it here. But if I had 1 molecule of aluminium sulfate, then I would have 12 oxygen atoms, 2 aluminium atoms, and 3 sulfur atoms in 1 molecule or 1 compound of aluminium sulfate. Because you see 2 aluminiums, 3 sulfurs, and 12 oxygens. If I had 2 molecules of aluminium sulfate, I would have, how many aluminiums would I have? I wouldn't have 2 anymore. I would have 4. If I had 3 of these molecules, I wouldn't have 2 aluminiums anymore. I would have 6. So I hope you see what I'm saying. You take your number of molecules and you multiply that by the number of aluminium atoms present in one of these. So I'm going to multiply that number by 2, and therefore my number of aluminium atoms will be 3,01 times 10 to the 23 aluminium atoms. So to get atoms, you always take your number of molecules, your big N, and you multiply it by however many number of atoms there is in the compound that they give you. Particles of aluminium sulfate are bonded in a crystal lattice. Now, the reason why they're bonded in a crystal lattice is because aluminium is a metal, and my sulfate ions, that is a polyatomic ion. This is a non-metals, oxygen, sulfur, non-metals. So write down the following for this crystal lattice, the name of the crystal lattice. That is an ionic structure. Ionic structure. Now just take note of the question. They're not asking for the name of Al2SO43. We answered that already earlier. They're asking for the name of the crystal lattice. It's an ionic structure. The particles of which it consists. Well, because we've got aluminium sulfate, I mentioned now that it consists of aluminium, which is a metal. So that is, the particles would be your aluminium ions, that's Al3+, and sulfate ions, which is SO4 2 minus. So Al3 plus, SO4 2 minus. How did I know that? Because you look at the charges on the periodic table. It also makes sense because if aluminium has a charge of +3 and the sulfate ion has a charge of -2, in order to make this a neutral compound, you'd have to multiply aluminium by 2 and the sulfate ion by 3, and that's why in the name it goes Al2 because we multiplied by 2. So that's where that 2 comes from. And SO4 3, we multiply the sulfate ion by 3. That's where that 3 comes from. Instead of saying Al3 plus and SO4 2 minus, you could have said aluminium ions and sulfate ions. 2 physical properties. Now, because it's an ionic structure, it's an ionic salt, it's a crystal lattice, we know that the properties associated with that are brittle, hard, not very good conductors of heat or electricity, any one of those 2. Then we've got 500 grams of our aluminium sulfate is dissolved in 2 cubic decimeters of water. So we've got a mass, that's giving me mass. We know the molar mass of this thing, we worked it out earlier. And they say that we dissolved it in water. So this is a solute dissolved in our solvent. This is volume. They want us to first define concentration. So that's the number of moles of solute per cubic decimeter of solution. Think about concentration. The formula is N divided by V. It's the number of moles of the solute per, which means divided by, cubic decimeter of solution. So moles per cubic decimeter. Calculate the concentration of the solution. So we have this formula, or we can use this one, C equals M over MV. Now, because they're giving us the mass and we know the molar mass and we know the volume, I'm going to use this formula over here. So mass is 500 grams. We don't convert that to anything. It must be in grams. Our molar mass we worked out earlier, it's 342 grams per mole. And our volume must be in cubic decimeters, which it is. So that's 2. And we get 0.73 moles per cubic decimeter. You have to give your unit and you have to give it correctly, or you're not going to get your 3rd or your 4th mark. In this case, we get 2 marks. Top of the fraction, substitute, bottom of the fraction, and answer. If we wanted to use this formula, that would be perfectly fine, but then we'd first have to use this formula that I'm writing now to get the number of moles. So we would sub in the 500 here and the 342 here, and we would get N, and then we would use our N in this formula to get concentration. Question 6. The first step in the extraction of zinc from zinc sulfide, this is zinc sulfide, is the combustion of zinc sulfide and oxygen. So combustion is essentially reacting it with oxygen over there, and we have 2 products and they say plus energy. They give me a balance equation, which is great. They say, is the reaction above exothermic or endothermic? Give a reason. Now, just by the way, combustion reactions are highly exothermic reactions, but if you did not know that, the way that you can tell that from the given equation is they have the reactants, which are these 2 things, and then they have the products, and as part of the products, as part of the things formed, we have energy. That means that energy is released, and we know that a release or a net release of energy is an exothermic reaction. So a net release of energy is exothermic. Just think of exo, exit, and endothermic. Endo, take in, inside. Endothermic means a net intake or a net absorption of energy. So this reaction is exothermic. Oxygen gas consists of oxygen molecules. Define the term molecule. So a molecule is a group of 2 or more atoms that are covalently bonded, and it functions as a unit. The next question wants me to draw the Lewis dot diagram for the oxygen molecule. Now you need to know that oxygen molecule, they say O2, so that's great. They tell me O2. We know that oxygen is a non-metal. So we know therefore that O2 will be a non-metal bonded to a non-metal, therefore we'll have covalent bonding. So we know that when we see our final Lewis dot diagram, we're going to see that of a covalently bonded molecule, not an ionic formula unit. So we won't see brackets, we won't see charges in our Lewis dot diagrams. We won't see these things. Absolutely not. So how we do it is we know that oxygen has 6 valence electrons. 1, 2, 3, 4, 5, 6. Plus the other oxygen also has 6. 1, 2, 3, 4, 5, 6. They need to reach octet structure, which means they need 8. If this one has 6 and this one has 6, to reach 8, they each need 2 more. They each need 2 more. Because remember, they're trying to reach the octet structure. Their outer energy levels must be full. Because they need 2 more, they know that they can share with each other. Covalent bonding is all about sharing electrons, not transfer. So these 2 over here will be shared with this oxygen. These 2 over here will be shared with the oxygen on the left. So in other words, these 2 that aren't in a little pair at the moment will be pulled to the middle, and they're going to be shared with the respective other oxygens. So how we draw our final diagram, it's only for 2 marks, so they don't want this beginning step, they just want the final one, is we draw the other electrons that will not be shared in like normal. So that's like that. 1, 2, 3, 4. Those will not be shared. Then those ones that I circled, the ones that will be shared, we draw in the middle like this. So I hope you can now see the oxygen on the left has 1, 2, 3, 4, 5, 6, 7, 8 electrons. Complete octet structure. And the same thing for the one on the right. 1, 2, 3, 4, 5, 6, 7, 8. So basically they share 2 pairs of electrons. So that would be your final diagram, obviously without all the scribbles. Right, our next question is more difficult. So they say during the reaction above, we've got 7 grams of zinc sulfide reacting completely with oxygen gas. That means that this entire 7 grams will be used up. All of the moles of the zinc sulfate will be used up. So they want to know, calculate the number of moles that will be used up, the number of moles that will react. So we know that if we're given mass and we want moles, we use this formula. Our mass will be 7 grams. Our molar mass will be that of zinc sulfide. Now, if you look over here, the zinc sulfide has a big 2 in front of it. That big 2 over here is not included in our molar mass calculation. So our molar mass calculation will be the zinc atomic mass plus sulfur's atomic mass, which is 65 plus 32. Again, this 2 over here does not influence the molar mass calculation. Only the little numbers do, not the big coefficients. So that gives me a molar mass of 97 grams per mole. So it's going to be 7, which is the mass, divided by 97, which is the molar mass. And I get 0.07 mole. That is rounded off. Remember, you have to round off to at least 2 decimals. So if I wanted to leave this as 0.072164.9, blah, 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 I absolutely could, as long as I round it off. Okay, so that would be mole. There we go. Now the next question says, calculate the mass of oxygen needed. Now, just because I have 7 grams of this doesn't mean I'm going to need 7 grams of this. Absolutely not. And you could be thinking, oh, ma'am, you use that thing called the mole ratio, right? So the mole ratio, zinc sulfide to oxygen, is 2 to 3. So if I know the ratio, then I can surely work out how much oxygen I need. Yes, that is true. But if you're going to use the mole ratio, you need to first work out the number of moles of oxygen needed. So we want the mass of oxygen needed, but step 1, before we get mass of oxygen needed, we need moles of oxygen. And how do we get moles of oxygen? We need to use the mole ratio. So what I mean by mole ratio is we know that 0.7 moles of zinc sulfide will react completely, which means all of that's going to be used up. 0.07. So if I know how many moles of zinc sulfide is going to be used up, I can use that to work out how much oxygen is going to be used up as well. So the two things that we put into the mole ratio, we write down like that. And the mole ratio is the big numbers in the balanced equation. So 2 to 3. So 2 to 3. So we always write down the formulas of the things in our mole ratio. Then we write down the mole ratio in its simplest form. And then I know that, remember, this is a mole ratio. I'm going to write here mole ratio. So we don't put mass in the mole ratio. So we can't put 7 into this ratio. It's not a mass ratio, it's a mole ratio. So that means I need to put in the number of moles of zinc that reacted. So 0,07. And now I can ask myself, if this many moles of zinc sulfide reacted, how many moles of oxygen reacted? Now, the way that I do ratios, it's very simple. This is how I teach all the way from grade 7, 8 maths upwards. So what I do is, if I'm trying to work out an unknown in a ratio and I know this side of the ratio, you go up, you divide on the side, and you times on the top. So it's alliteration and it rhymes and stuff like that. That's how I remember it. So you divide on the side, you times on the top. So you go 0,07 divided by 2. You take that answer and you times it by 3. That gives me 0,105 moles of oxygen that was reacted, or 0,105 moles of oxygen that was needed. But did the question ask for moles of oxygen that was needed? No, it asked for mass of oxygen that was needed. So if I have moles, remember moles is N. If I have moles of oxygen, how do I now go and work out mass of oxygen? Yes, we use this formula. I have the moles of oxygen. I want the mass of oxygen. What do I put in big M? Well, we work out the big M of oxygen, which is 16 times 2. Why 16? Because that's the atomic mass number of oxygen on the periodic table, the big number. Why times 2? Because O2, oxygen is diatomic, there's 2 atoms. So that's 32 grams per mole. So we're going to take our number of moles that we just worked out, 0,105. We're going to take our molar mass, which is 32, and then we can work out our mass. So 0,105 times 32 will get me my mass. And I get 3,36 grams. You need to remember your units. Now, just as a disclaimer, if any of you have done this paper before, or you go look at the memo, your answer may be slightly different depending on your mole value that you used over here. So remember in 6.4.1, we calculated the number of moles of zinc, and I rounded it off to 2 decimal places. And I said you could round it off, or you could keep all of these decimal places. So if you decided to round it off to more than 2 decimal places, which you are allowed to, if you decided to keep all of these decimal places, then you're not going to have 0,07 over here in your ratio. You're going to have a longer decimal. That means you're not going to get exactly this decimal for oxygen, moles of oxygen. That means you're going to have a slightly different number here, and your mass value may range all the way from 3.36 to 3,46 grams. It just depends on which decimal version of the number of moles you used. But because this is a new question, so they asked you to calculate number of moles of ZNS, and we got 0,07, and we rounded it off because we reached the end of a question. You may use a rounded off version in the next question, but you may also use a non-rounded off version. I hope that makes sense. Right, in 6.1.6, they want to know the volume of SO2 gas produced at STP. Now, as soon as you see these two things, a gas and STP, your mind needs to go to this formula. This is the formula that we use to work out volume of gas, especially at STP, which is standard temperature and pressure. And when we are at standard temperature and pressure, Vm is 22,4. That is on your formula sheet. So if I want to work out the volume of a gas and they say STP, this is where I want your mind to go. Now, in order to work out volume of SO2, okay, sulfur dioxide, producer STP, I know that Vm is a constant. I'm looking for V, so I need number of moles of sulfur dioxide. But how do I get moles of sulfur dioxide? Well, we need to use our mole ratio again. So now you might ask yourself, what do I put in the mole ratio? Well, if we read the question carefully, they say that the zinc sulfide will completely be used up. This is basically the limiting reagent, which you will learn about in grade 11 and in grade 12. The limiting reagent is the reactant that will be completely used up in the reaction. And the limiting reagent determines how much product I produce. Okay? So it's kind of like if you make a hot dog roll and you have 3 hot dog rolls, but you only have 2 sausages that you can put on each roll. How many complete hot dog rolls can you make? So if you have 3 rolls, so these are the rolls, but you only have 2 sausages, technically you can only make 2 complete rolls. So the sausages, is what we call the limiting reagent. And we can see that the amount of the limiting reagent tells me how much product I make. So how that relates to chemistry is we know that zinc sulfide, ZNS, that is going to be completely reacted, which means that that's my limiting reagent. That's going to run out first. So my zinc sulfide will determine how much product I make, how much SO2 I make. So in order to find out the moles of SO2, the amount of product that I make, I always put that in a mole ratio with the stuff that's going to be completely used up. This is a difficult topic. So if you need to rewind the video and re-listen to me explain that, you do that. Basically, the reactant that's completely reacted or the reactant that is used up in the reaction, the limiting reagent, that is the one that we're going to put in a mole ratio with my products. Okay, because the limiting reagent, the one that's used up, will determine how much product I produce. Now, which numbers go into the mole ratio? Well, remember, the mole ratio is the big numbers. So 2 to 2. So if I put 2 to 2, how do I simplify a ratio of 2 to 2? That would be a 1-to-1 ratio. So what that means is if I completely react 10 moles of zinc, that will produce 10 moles of sulfur dioxide. If I react 1,000 moles of zinc sulfide, that will produce 1,000 moles of sulfur dioxide. Okay, because it's 1-to-1, exactly the same number that is reacted will be what is produced. So if you can remember correctly, from one of the first questions we did is we figured out that 0.07 moles of zinc sulfide would be reacted. That means, therefore, 0.07 moles of SO2 will be produced. Now, we're not done with the question there. The question didn't want to know how many moles of sulfur dioxide is produced. They want to know the volume. So now how do we go from moles to volume? Well, we mentioned that we're going to use this formula and it's at STP, so we know Vm. Therefore, my number of moles of sulfur dioxide is 0.07. My volume is what I'm looking for, and my molar volume, because it's at STP, is 22.4. So how we solve for V is we say 0.07 multiplied by 22.4, and I get 1.568 cubic decimeters. Now remember, if we decided to use that long decimal, that unrounded off number over here, which was that number, and we multiplied that by 22.4, which we are allowed to do because we can use the rounded off version, we can use a longer version, then you would get 1.62 cubic decimeters. So they'll accept an answer in that range. I will say again that because we worked out the 0.07 in question 6.1.4. And then we use that number in 6.1.5, which was a new question, and 6.1.6, which is a new question. You are technically allowed to use the rounded off version. But if you would prefer to use this fraction or the unrounded off version, you are more than welcome to, because it is technically more accurate. I hope that was helpful. Let me know what else you want to see in the comments. Please give this video a thumbs up, subscribe for more maths and science.